And we are recording from now. So everybody, welcome to week number 11 out of 13. So let's start as we usually do. Yishiberach Avotenu v'Amatenu Abraham, Yitzchak v'Yaakov, Sarah, Rivka, Rachel v'Leah. Yivarech v'Yirapeh et kol choleinu u'bneihem. הזקוקים לרפואה שלמה. ברור שאנחנו מתפללים להחלמתם. פסחה זה הקדוש ברוך הוא ימלא רחמים עליהם, להחלימם, לרפאותם ולהחזיקם ולהחיותם. וישלח להם מהרה רפואה שלמה מן השמיים עם כל חולי ישראל. רפואת הנפש ורפואת הגוף. השתה בעגלה ובזמן קריב ונאמר אמן. טוב, what's on today's menu? אז ככה. We started talking about linear sorts, yes. And we talked about counting sort, and we talked about radix. And today we're going to add the third one, which we had said there's 10 altogether, and that's called bucket sort. We'll be seeing that. And we'll be doing exercises about all the sort methods, doing a proper recitation session. We'll do quite a few exercises to be able to understand more fully these sorting methods, which you started seeing last week. Now, this order that I had here was based on Menachem. We're going to talk about rotations in a minute. We'll do that first. And then we'll be talking about what's next. What's the program for the next 2 weeks? That's bigadol what's happening. Okay. So I just want to talk for a minute about rotations. Right, this is a slide from when we talked about rotations. If you go to some of the materials in Hebrew on the website, or even if you go to some other places somewhere in the web, you'll see there's sort of like a machloket between how we sort together, how we sort in this topic, and how it's presented there. It's a machloket, which is not, it really depends how you're looking at things. And I'll explain and you'll see what we're talking about. Let's take this example, right? Okay, we saw there were 4 different positions where you can have an imbalance and you have to start doing a rotation. We saw that if we add to the left, you have to do rotation. And the rotation I have to do is a right rotation. But this is the case. The case is basically, we can say it's a left case. The case is left to the left, and the rotation is to the right. Now, you'll see in a lot of different materials, especially in some of the lecturers here, they'll say that they'll say, okay, you're doing a LL rotation. LL meaning the case and not what actually the rotation that you're doing. Again, I'm making a distinction between what's the case. What are we calling the case? The case is LL. The correction is RR. The case is LR. That's the case. The correction will be RL. Now, I presented it to you, which I think is in a more correct way. You don't get confused because you're doing a right rotation. That's the rotation you're doing. Rotation is no machloket. This is a right rotation and this is a left rotation. There's no machloket about that. So it's easier not to get confused. And fortunately, I can see that most of you weren't getting confused because we said, okay, this is the condition, this is the case, and this is the correction. The correction is a right, left. And that's the rotations that we're doing. In the exam, if you're asked to build a heap or whatever, and you have to do some type of rotations, then you can definitely put on the arrow saying you're doing a RR, meaning you're doing a right rotation. And you can see, and it helps you when you're going stage after stage. Okay, I don't have to remember, it's LR, but I'll really have to do a right left. And I get really confused, especially with the double rotations. Single rotation, maybe nicha, you can get away with it. But with a double, you don't want to have that confusion. Now, there's a lot of poskim that go books that go according to the way I presented it. And there are some the other way. The Chumash, Korman, does not really talk about it. Korman has maybe half a page about AVL. He does talk about rotation somewhere else when he talks about a different type of tree that we don't learn in this course, we learn in the next course. So that's our understanding, that's how we're working. So in case you do get to some type of internet site and you see that it's reversed of what we're talking about, it's reversed and not reversed. It means that they're saying that LL is, they're calling the rotation a LL rotation, but what you're doing is the right one. So confusing, so yes, and it's confusing.
Our way is that if it says RR, then we need to correct it by doing left?
No. RR is the actual rotation that you're doing. The case is left-left. In the case of a left-left, you want to rotate the grandfather right. We're always talking about a triplet, right? And we have the three values where we want the middle value to be in the middle. Right? That's the whole concept of rotations. Right? We're going to always rotate here, the grandfather here. So if we're doing that, let's do it this way maybe. So if we're rotating this grandfather, right? So we're rotating him right. The case is left-left. Yitzchak, okay now or not?
Yeah.
Okay. No, it's very, very important to understand. We're differentiating between the case, let's talk about the Morish. The Hechatimse, you have the Hechatimse, and what is the solution for it? When we say RR, RL, LR, all those, that is the solution of the Hechatimse. Okay?
And on the exam as well, that will be the case?
Yes. Especially since I'll be marking the exam, so even more reason, not a problem. Okay? Fine. So that is something that came up. Okay, Menachem, is that a clear explanation now?
Yes, thank you.
Okay, good. Menachem, just so you know, Menachem brought it up. But not only Menachem, I also got a query from a student from Machon Tal in the Hebrew speakers that studied by me last semester in the Introduction to Computer course. And she saw that there was this stira between how I presented it and how her lecturer presented it. So I saw that it was coming up, this problem. So it's important to make this clarification. Okay, so that was first thing. Next, Mara Mekoimes. Do you know what Mara Mekoimes are, rabbis? Do you know what Mara Mekoimes are? What's Mara Mekoimes? You don't know. Anybody?
Something that shows you where you should be learning from.
Yeah, good. Mara Mekoimes. That's what we learned in Yeshivish. So there was somebody in this course, in this group here. I could say it because Nishvachol, is he here? There you go. Yes, he is here, isn't he? Pinchas David, you're here, right?
Yes, thank you.
Yes. Okay, so Pinchas David asked, can I give you references to the Chumash, the Korman, the book, according to our different topics? So I did prepare that, and let me just show you. Let's just do here. And what I prepared, it's on the website already. You have here, this is the name of the book, right? There are PDF things floating around also the internet. Also on the drive, I think of the Machon, somebody put it up with the students. And obviously the actual physical books, and Pinchas David can tell you how heavy it is. It's a big book. A lot of it is not relevant for this course because the name of the book is Introduction to Algorithms. It's not a data structure book. There are a lot of good, very good data structure books. And definitely I recommend as English speakers, go into the library, those people that are on campus, go into the library, look around for the data structures, a whole slew of books. Sometimes it might be data structures in Java. What's the difference? It's pseudocode from your point of view. You know how to read code. So you don't need to know all the exact businesses of the syntax. That's not a problem, especially if you know C++ in the object environment, then it shouldn't affect you. There are some very good books, Sedgwick, there's a lot. But obviously, like we said, this is the Urim V'Tumim of the course. So what I did is I took the topics and I sorted it. I sorted the topics. Here we get example of sort. I sorted the topics according through the ABC, right? So there's no logical connection, according to the order here, just different things. I bring to your attention Fibonacci numbers. Here he explains what I said about the mathematics, about the whole thing of using phi when you're using the approximation for Fibonacci numbers. Actually, we'll be seeing that again today a bit from a different point of view. So there's two pages. That's it, or a page and a half. AVL, like I said, 333 is half a page. So it's based on this book, the third edition, as they say, Gesundheit. So that was for you guys. And thank you for Pinchas David. Everybody says thank you, Pinchas David, for your day.
Thank you.
Okay?
Professor, which sort did Word use?
Just Word?
To when you put this in alphabetical order, unless you entered
which sort is sitting behind? That's an interesting question. I don't know which one they use. It's very, very, in the Microsoft, I don't know which one they're implementing here in the Office suite. A lot of programs use Quicksort as their sort of by preferred sort. Why did they do that? Because in the expected case, we know that in the worst case, Quicksort is n squared. But the expected case, the normal expected case, we know that it's, it's n log n. And because it's also in place, that it doesn't take extra space, that's very preferable, let's say, to merge sort, which is also n log n, but it takes extra space. You'll find if you start looking behind scenes, you'll see that Quicksort is definitely one of the ones that people prefer using. It's nice, and there's also fetches, a lot of fetching that you can make it even perform in the group of n log n. If you do it this way, you can get better performance. Which we're looking here at our level of the course, really at the order of magnitude, right, of the actual sorting methods. But when you go in, you can start making, okay, in the n log n, I can improve it this way. I can get rid of a couple of swaps. I can get rid of some comparisons. I can optimize the algorithm, but it's still the same order of magnitude. But obviously, if I can optimize, I want to optimize. I'll be showing you with one of the exercises we'll be doing today. You'll see the concept of optimization with that idea. But okay, when we get to that. But yes, that was
I have a quick question.
Yeah. Rega, Eli, 1 minute. Did you get an answer? Whoever asked?
It was Yoni, yeah.
Yoni.
I was just wondering about the stable. This is a prime example. This would be a great example of needing a stable sort, right?
Yeah.
Because you have the pages follow on the left side.
Right, exactly. Because what you have to do is that you, like in Excel's classic example, where you're taking the columns, or here, I took both columns and I sorted it according to this. So if it wasn't stable, you're fair, great. If it wasn't stable, the pages wouldn't be correct. Excellent. Yofi, good example. Yes, Eli, you wanted to ask something.
Yeah, just about the efficiency of Quicksort. Wasn't there a possibility, maybe I'm remembering wrong, but wasn't there a possibility that Quicksort was actually n squared, depending on...
Yes, yes. We said that in the worst case, There is a worst case, which would be n squared. The worst case would be that the numbers are already sorted, and you're taking for your pivot value always the last value. So what will happen is that you'll have, it won't be sort of like balanced. It will be skewed, that the left-hand side you will have maybe one value behind to the left of the pivot, or none, and everything else will be to the right. And then it will work out to n squared. The whole assumption is that we're going to try as much as possible. That's why the random pivot concept is even the better one, where randomly, and if you do these permutations, it will work out to be log n times, because we want to hit the middle as much as possible to divide each thing to two equal parts. But we're dividing to two, but we want two equal parts. Okay? Ellie? Yeah? Good. Excellent. Yossi. Okay, so now what we're going to do is go back to here.
But just on a side, I
Yeah.
remember Professor Stolman,
Yeah.
last year for the course, he said something like about, I think is what he said, if I remember right, Word, or maybe it was Excel or something in in Office, use quicksort up to 27 nodes, items. He said that at that point, that's when the graph becomes
Yeah.
worse and it goes to different sort. He said he claimed something like that.
First of all, out of knowledge, I have no idea, but the sphora there, it makes sense what he's saying. Yes. Mm-hmm. Okay. Just like insertion sort, we know that if n is less than 50, then it's much quicker. But there are certain cases where we know that it's more efficient in certain cases, besides it being sorted, obviously. Okay, that was two things. Right, let me just mark off that we talked about them. We talked about our rotations and the reading list. Okay, so one other question for everybody. Sorry, still not over this. Did anybody go to that site that I showed you about algorithms with attitude? Did anybody go and look at some of those films, the short clips? Nobody?
Not yet.
Not yet. Nice, thank you.
Saving it for the final.
Okay. No, I'm just curious to hear feedback if you find them good or not. I found them, besides entertaining, very quite clear and concise. And I just remind you about that. The link is in the website in the beginning there, where it's the general materials in the ESP area. Okay, so I got to answer to that. Sorry. One other thing I want to remind you, I'm reminding you again, if somebody here feels that they need some type of extra coaching, extra help, some type of chomech or something, you can write to me in private on the chat or send me an email and we can see how we can try to help you. Theoretically, the office of the ESP is supposed to be in contact with people who have been asking and they're making shidduchs. If it's not working out through the ESP office, come back to me and tell me, and then I'll see how I can accelerate, that's a good word, accelerate the process, because we're coming now to money time towards the end of the semester. We have other courses as well, and obviously I want you to do well in every course, but especially in this course. Okay, so let's continue. We talked about linear sorts. Just as a reminder from last week, we talked about counting sort, and the idea of the counting sort is that, ooh, that's a zero? Or, oh, that looks like a zero. Oh, okay. The idea of the counting sort is that, first of all, it only works with whole numbers in a certain range, between 0 and k, and we saw how it works with that whole nice idea about counting, and then we even saw how it works that why we're doing it from the how we count and what's the whole idea of the cumulative index in order for it to be stable, which was very important for us for it to be stable. And it is a stable one. Obviously, it's using extra space. Okay, that's very nice. Great. Then we saw another one, which was very interesting, which was the radix sort, which we said is sort of like a wrapper, because the radix sort itself calls counting sort. So the additional memory needed, depending which stable sort. So if it calls counting sort, then obviously it's not going to have, it will have additional memory, and therefore if it's in place, it depends, but it will be stable. Very important for us to be stable. We said why, and in exercise, the second exercise that we'll do today when we start practicing and doing exercises, we'll see an example. I've built an example to be able to see it mamish. So that's something that also we'll be seeing. Why it's important for it to be stable. And the key, and that's the most important thing, the key here is a number of digits in base B. And we have a certain amount of digits, D digits. Now, base B could be base 10, obviously. However, they're whole numbers. The key has to be a whole number. It can't be a decimal number. Now, theoretically, you know what, let me ask you, why can't it be a decimal? Why can't we have it a decimal? Why can't I sort 3.1415 with 2.72, with 1.618? Why can't I sort these numbers with a decimal point? Anybody? It should be.
I mean, you could if you just multiply it out that many places, and then you could put it back after or something.
Why do I have to multiply it out? We're doing a radix sort. A radix sort takes the digit. So I can get to that digit every time I get to that digit, just like I do the digits in a whole number. So I'll take, let's say they're all two digits after the decimal place. So I'll take the second one, then I'll take the first one, and we said we go according to the LSD, right? The least significant digit. The least significant digit happens to be, let's say in base 10, 1 divided by 100. The second one afterwards. What's the difference?
The decimal is not part of the base system, is it?
Why not? Sorry. You have a 10 to the power of 1. What's what we call it? Ones, tens, hundreds, right? What does that mean? 10 to the base of 0, 10 to the base of 1, 10 to the base of 2. When you have 0.3, what's that mean? It's 3 times what? 1/10. What's 1/10?
10 to the negative 1.
10 to the negative 1, 10 to the negative 2. No problem at all. So on paper, theoretically, it should work. The problem here is now here, when we actually get to the implementation on a computer, we have a problem.
You can't really take a mod of a float.
Yeah, okay, you're hitting the main aspect. When did you learn how floating point numbers are represented in the computer? This semester or last semester?
This semester.
This semester in architect in the Mivnei HaMachshev course, right?
Yeah, a couple weeks ago.
Okay, a couple of weeks ago. Good. So you learned how a floating point is represented in the computer with the mantissa and this, the two parts, right? So
yeah.
The algorithm won't work because the representation is not a series of integers like as we know it. So it's going to be very hard to implement it unless you start saying, okay, I'll do a radix sort in a certain way for before the decimal point and after the decimal point. It starts becoming very, very tricky because the way the thing is represented. Now, it is true that there are, I'm just throwing out if already, there are standards by the IEEE about relation to floating point numbers, They have put out standards. And then if you know that the numbers according to this standard, you can build your specific sort for that. And then basically you'll say, why do I need this? Let me just use somebody else instead. Okay? But in principle, it's only whole numbers. Okay? Oh, one other aspect there is also, how does it deal with negative? Think about it.
Couldn't you make,
Again, because when you're representing in the computer, you have that, the sign flag, -1, 1, 1 and 0. 1 means it's negative, right? Remember that? Guys? Signed numbers, unsigned numbers. You learned about that a bit somewhere.
Yeah, plenty.
Okay, so that's something to take into account. Okay.
Why 26 though? Can you
Why
give us some insight?
Where's
Or
27?
27? I'm sure maybe it was 27 you said?
Where? In relation to what?
You said last week that
Yeah.
mode.
Yeah. Okay, tell me why.
I don't know. I was asking.
Okay.
I would guess, maybe I'm wrong though, it would have to do with the size of a word perhaps?
No.
Okay.
Okay. Good thinking, but nothing connected. When we get to exercise, the third exercise that we'll do today, we'll be talking about, I'll be demonstrating that. But I know those are things that we still have to, we talked about it in general, but we have to drill down. And so I built the exercises accordingly so that we could see these, actually that point. Excellent, thank you. So you're giving me positive reinforcement about the exercises I chose to do today. Excellent, thank you.
I have a question.
Yeah, Ronnie.
Isn't it possible to implement radix sort in a way that we could sort floating point numbers by kind of sandwiching the algorithm with a multiplication by 10 to the power of whatever, or whatever your base is, that to the power of whatever. So you get the number essentially out of a floating point representation, sort it, and then at the end, you put it back in floating point representation.
Right. First of all, yes. But then again, if we're looking about the runtime, okay, so basically you're saying that I'll have to do O of n, in O, I'm going to have to go, I'm adding a complexity of twice O of n, or theta of n. Okay, so in relation to the overall complexity, we didn't add to anything, because it's n. But you are adding, but in the actual runtime, when looking at runtime, you're making it more complex. It's not optimum. It's doable. I'm not saying it's not doable. Okay.
Especially because multiplication and division are heavy on a processor, right?
Not really anymore. There are processors, a lot of the CPUs that they have a multiplication already built in. It's not only adders. It's not only half adders and full adders. If all those are things you learned last semester, right?
That's what we're learning now.
Oh, you're learning that now. But you have built-in multiplication already in a lot of the processors. That's not the problem. But from the algorithm point of view, I'm going to have a loop for 1 to n, right? That's a loop. Do it on all those n numbers, multiply it out, and multiply. Okay, so say the actual cost of multiplying it out is O of 1, and the putting it back into a decimal form is also O of 1. But you're going to do that n times each time. So you are adding a certain extra commands, which makes it more bulky. But again, it's still in the framework of O of n, for sure. There is radix sort, and I'm very mitlabet. I haven't made a decision. I wrote it down to talk about it. Yes, no, I haven't decided. If I do, I'll mention it next week, not this week. There are radix sorts. Again, once you start going and reading material about it, you'll see there are radix sorts that you start from the MSD, not from the LSD, not from the least significant digit, but from the most significant digit. There's nafkaminot lahalacha. There's definitely nafkaminot. You could think about it. We're doing the radix sort, which is LSD. But if you do a Google search, MSD, radix sort, I'm sure you'll get a lot of hits.
Professor, but
Yeah?
Sorry to interject, but according to the way you presented it last week, that should be impossible. I remember somebody even raised that question.
Yefet. No, okay. The question is, how do you do the MSD one? Right? There is a version, which is the MSD version.
And it's stable?
No. Okay, so first of all, straight off, it won't be stable. So you can say, okay, look, if I'm not worried about the stability, let's say they're all distinct keys. No, distinct keys won't be good enough. It makes no difference to me. I don't need to know the stability. I'm not interested in stability. But then, will it work or not? There is, exactly, now you're seeing why I haven't presented it. I think it's more, it's not in the syllabus. So I decided, okay, we'll do the LSD according to the syllabus. And if we had more time, or if we were in the classroom together, maybe I would have done something, but not, for sure not in our environment now, because it's a bit more complicated. But just I'm throwing it out to you that there is a version called MSD Radix sort. And with no further ado, or whatever it's called, DDDD, bucket sort. Now, already I'm going to tell you a machloket. Bucket sort. In Hebrew, it's called miyun dli. The Americans here will call it a bucket. It's a bucket. Pinchas David, what would you call a bucket in English? Are you here? Are you still here, Pinchas David?
Yeah, it's just my space bar not working. No, we call it bucket as well, sure.
But there's another word for it. When you want to throw something in the rubbish, what's the rubbish? The rubbish?
The rubbish bin.
Bin.
Right.
In America, they use the word bucket more, and we call it the English speakers, sorry, the Anglo-Saxons, let's call it, use the terminology bin. So you might see in some places the name bin sort. Definitely, I'm using bucket sort because, first of all, the Chumash uses it. It's an American book. But over and above that, it doesn't confuse you because you might see bin sort and you might think binary. So it's good after using the word bucket sort, but you might see a bin sort, not to confuse it from a binary search sort. Again, like we said, there's a lot of different names floating around, but you have enough seichel to understand what's going on. Okay, so how does it work? Obviously, to become a linear one, it's going to need a very specific type of key, as we saw, because we don't want to do it according to comparisons. So we're going to assume that all the numbers are basically decimal numbers between 0 and 1, not including 1. I remind you, if you don't notice, this is deliberate. It's rounded here, and these are square. All right, mathematically, is everybody clear what this means?
Yes, it's a map.
Right.
Like set
Right. This is including, and this is not including. Right, not including 1. So we're assuming all these decimal numbers. But read carefully what's the definition. What else do you notice here?
It's uniformly distributed.
Uniformly distributed. Now, most of you, or a lot of you, some of you, never learned probability or statistics. Maybe some of you, Shana Bet guys, maybe have done it already. And maybe some of you might have done it in high school at this level or whatever. So I'll be talking very intuitively in relation to distributions and probabilities and not go in too much of the heavy maths because we don't need it. But the idea is, just like it says here, uniformly distributed. We expect that if I have n numbers, then if we divide them into, let's say I have n numbers, and I divide it into 5 groups, for example, then I'll expect there will be n divided by 5 elements in each group. For example, I have 100 numbers, and there's 5 bins, buckets. So we expect if I divide them into ranges like that, into bins, we expect to have 20 in each one. That means it's uniformly distributed. And the base of the whole bucket sort is based on this distribution. There is a version where we can assume uniform distribution of the keys between 0 and k as whole numbers. But again, that's another version which we'll be talking about today. I'll be showing it to you. But the whole concept is that we have a uniform distribution. It uses extra memory. If you notice, all these types of counting sorts, this way or that way, a counting sort, a radix sort, and a bucket sort has some type of element of counting this way or that way, or doing something like that. And they use extra memory, and that's how we make it more efficient runtime, but memory, it costs us. So Dafka here, it's going to be reversed. The auxiliary array will be called B, from 0 to n minus 1, n being the number of elements in A, in our original array. And C is where we're going to have the answer. In place, obviously not. And I'm already telling you now, it is stable. Okay, so now, if we were in class, I would have done a whole thing with PETEX or bring buckets and throw balls in it and stuff, but we're not there. So I had to go and build something. So I built up this demonstration. Now, this is just to get the general gist of the idea, the concept. Afterwards, we'll drill down and see it actual with the algorithm, and we'll do it properly. But I just want the idea. The idea is, here's my original array, A, and all of these decimal numbers. My array B is an array. It's an array of what?
Pointers?
Of what? Oh, fair.
Pointers?
Why do you say pointers?
Just based on the fact that you got slashes there, I assumed to denote null pointers.
Good. There's no zeros here. It's not integers. Actually, my array B is an array of lists. Right? And I'll take it further than you said. Obviously, a list is the pointer to the head of the list, right? The heads of the list. So right now they're all empty lists. So in the beginning, I have my array B, which is all empty lists. I take the first value, and I'm going to take all the values, that's the first stage, take them and insert them into the appropriate bucket. For now, the appropriate bucket will be according to the first decimal digits, 0.2, 0.3, right? So basically I have here 9 digits, 10 lists from 0 to 9. And according to here, let's put it in as 0.25, insert it into this list. So the list will look like this now. 0.37 shows up, put it in. 0.21 shows up, just add it. 0.45 shows up, add it. 62, 51, 32, okay. 64, 91, 67, 82, 35. There was nothing starting with 0.0 something or 0.1 something. It's not very, very uniformly distributed, right? If you notice, I have 2 here with 3, and here there's 3 things that without anything at all. There's 12 numbers here, I think. 2, 4, 7, 8, 2, 5, 6, 7. Yeah, there's 12 numbers here. So distribution's not bad, but it could be better. But that's not what's interesting for me right now. Is I want to show you the concept, how it's working. So that's the first stage. What would be the second stage? Sorry, yes?
I just want to clarify. Is this a sort that you need it to be uniform, or is testing for uniform, or is
No.
uniform?
The values have to be uniformly distributed in order for it to be linear. Because if it's not, you'll see in a minute why it's not. But we're assuming that there is some type of uniformity in the distribution.
Is our list considered uniform?
What?
Is the list we're using right now considered uniform?
We have multiple lists.
Just pachot or yoter, yeah. It's a small n also, but it's on the gvul. Yeah, it's okay. Yes. It would
It's
be.
important to know if you want to know if this is the best sort to use.
Sorry?
It's important to be aware of this if you want to know if this is
Yes,
the best
sure,
sort to use.
definitely. Therefore, the whole idea, what's happening here? I know what. The whole idea is that you have a whole slew of sorting methods, and according to the different shikulim, the different, what's a shikul in English?
Consideration
Considerations, thank you.
or needs.
Yeah, needs, considerations, you'll choose which one. Do I need it space efficient? Do I need it time efficient? Does it have to be stable? How does it deal with random elements? What happens if it's almost sorted? Is this better or not better? I mean, there's a lot of different considerations. And one of the considerations to be able to use the bucket sort is that the data has to be, or should be, to use it efficiently, the data has to be uniformly distributed. Okay, that was the first stage. What would be the next stage? Who wants to
Sorting
guess?
Or independent lists.
Okay, so the second stage will be sort the buckets. Take a look again. Let's say look at the this list number 2, or list number 2 and list number 3. Look at them. Look, this is the eye check. We're testing your eyes now. Okay, everybody see? We sort each list. We sort the buckets. How? In a minute. We're sorting them. I've sorted them now. What's stage 3?
Putting it in the CRA.
Yeah, concatenate them. Put them in, just start copying them over to the C. Boom, 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 according to, here. Loop through B. And in each list, copy them over until you get to the end of the list. Well, not end of, you're not at the end of the list. And then boom, 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 boom. Copy them over. That is bucket sort, the idea. Okay? Visually to help you understand who's against who.
And if we wanted to use this on numbers bigger than 1, we would just divide it by, or
Okay, yeah, I'll be showing that in a minute. Okay, good, excellent. You're right. Good point. We'll talk that in a minute. So let's look at the algorithm first. The algorithm in this case gets A. You can also see A comma n, where you're given the number of elements, or you can just say n is the length of A. Obviously, 2 different versions, it's the same idea. So we know that we have the array A, and n is the number of values. So the algorithm is very simple, reading it. Okay, go through all the numbers in A and insert AI into the bucket, an appropriate bucket. Pseudocode, it's lovely. You know, this command here is, might be a bit more intricate, but very nice. How do you insert it? But pseudocode. Now, what's the bucket? Which bucket? Now, take a looky. The floor of n times AI. Now, what happens is like this. What's the idea? Why do I have to do that? Why n times AI? Question mark at the end of my sentence? Anybody?
Well, if we said it's a decimal, but the buckets are not, 0.1 bucket, 0.2 bucket.
Excellent. Obviously, the indexes of an array are whole numbers. So we have to take this number, we'll multiply it by n and take the floor of it. And that will give us the index of which bucket to put it in. Stam, for example, in the previous example, my n was 12. And if you take 0.25 and multiply by 12 and take the floor of that, if I'm not mistaken, you'll get to bucket number 3. Okay? So each value will get into its appropriate bucket according to that that computation.
I didn't understand.
Yeah. What you want to know?
I understand this BNAI.
Okay. You want to put the value AI into the array B. Okay? Now, in which list do you want? So here in B, you have B, and I'm expecting to see an index here. What's the index? The floor, so that's a whole number, of n times AI. AI is a decimal number. I'll multiply it by the number of elements in the array. And then
Can you show us on the list? Could you show us
Sorry?
in the example? Could you show us from the example before?
Yeah, sure. So basically, that's why I'm saying this example is not 100% according to the algorithm. Because here, I took the 0.25 and put it in number 2. According to the algorithm, it should be here in 0.3. But I didn't want to confuse you guys. I wanted at first just to understand.
Why not multiply just by 10 and then floor? So that way 2.5 will go to 2 and 3.37 will go to 3.
It will make bigger buckets.
Oh, okay.
It will make I'll have more elements in each bucket. I want to get the optimum. If you think about it, the optimum, if it's really totally uniformly distributed, I'll have only one element in each bucket. That's really best case. You with me?
Of course, yeah.
That's the chap. I want to make these lists as small as possible. And therefore, the sort here is not going to cost me anything. The worst case is that I have almost all the elements in one bucket. To sort that one is going to cost me. But if this is going to cost me nothing, if at all, no, it will cost me something, then that's the whole beauty of it. Okay? So what I showed you here was just to be able to understand the concept. The actual correct equation to compute which bucket will be the number of buckets. Therefore, that's the reason why, if you notice, when we talked about the size, when we talked about the size of the auxiliary array, is we're going to have n buckets, n lists, according to the number of values. Now, it is heavy from our point of view of memory. It's taking extra memory. That was the price of having this as a linear sort. Yeah, I still haven't proved to you that it's linear yet. Okay. So after we put them in the appropriate buckets, look at this. Sort each bucket, each list sort using insertion sort. Ding, 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 ding. What's insertion sort? Insertion sort is a comparison sort.
Also comparison.
Nachon?
Yeah.
So how can I write that? How can it be linear in the end? So the answer could be it's not linear. No, it is. But why?
Because you have evenly distributed buckets. So even if we have, 2 in there, at most it's going to be a swap, maybe 2.
Different. Okay. First of all, we know that insertion sort, in the best case, is O of n. All right? If you remember, in insertion sort, we saw that it's O of n. So that's already a reason.
Wait, why is insertion sort O of n? Because
in the best
each
case.
item. I know, but why? We're just taking
Because
each
you
item.
won't have to. How does
Right.
insertion work? And you might have to move people, to make place to put it in. You're inserting. But let's say it's all sorted. Let's say the numbers are sorted. So you don't have to do that extra loop. It never goes into that loop of moving everybody to make place. So basically it's O of n. Okay? Or even theta of n. Let's say that. Now,
I'm assuming we picked insertion sort because it's in place.
one, because it's in place, and also because of the algorithm, we can have it. It will be worst case n, because the number of values is very, very small in each bucket, right? Because of that distribution, it's going to be maximum O of n.
Will any sort be the maximum of ON for the same reason? That even if it's bubble sort, if there's only two elements,
yeah, but insertion sort, bubble sort will have to go do that double loop. Insertion sort, I don't have to go into a loop. If I don't have to move anybody, I don't have to move him. Bubble sort will do those, n times n squared, n divided by 2 iterations. Insertion sort doesn't always go into that loop. Again, we're talking about optimization here. You could put here bubble sort, but then it's making it much more complicated. Also, to do a bubble sort on lists is much more difficult than doing it on the insertion sort on the list. Insertion sort is much easier to do. Sorry.
You're saying by 3 already. If the n is already equal to 3, there's already significant difference because n squared is 9. And if it's insertion sort, it could be just 3.
Yeah. Well, I'll show it to you. And you're right, but I'll show it to you a bit more mathematically in a minute. Let's just look at the third stage. The third stage is, okay, take all those buckets and concatenate them, which is just start, like I demonstrated, just start taking them down. Now let's look now at the efficiency. And this is the kicker. Let's take a look at the efficiency. This loop, okay, that's n. To insert it into, that's n, that's theta, it's O of n. Now here, what do we have here?
another loop of n.
Now, it says sort bucket. Now, take a look at this. One bucket's going to cost me. Now, this is the mathematics that I didn't want to get into too much. Is, wow, this is not good. I want to make correction in a minute. Is O of 2 minus 1 over n squared, 1 divided by n. Now, how did I get to this? The average sort time of all the lists. Of all these lists, what is the average sort time? The average sort time is definitely something that we have to think about. There's a whole mathematics behind it. If you're really interested, you can look it up. But the idea is that because of the distribution, and there's a function of the binomial distribution, then you can definitely see it works out to be O of 2 minus 1 divided by n. That is the actual equation. Okay, now
that's saying the average bucket's going to hold 2 elements only?
No, it's not that. Okay, I'll give you a glimpse of how it gets to it. Is that 1 divided by n is the probability, that's the p, of which bucket's in, right? 1 divided by n, because theoretically, if I'm distributing it equally, so that each bucket will have 1, and there's n buckets, so n elements, so it's 1 divided by n. So definitely that's something that we'll consider. Sorry, I'm just writing down something here. So the 2 minus 1n is a whole mathematical, really, it is based on the probability and the shonut. What's the shonut in English? We learned statistics already. Shonut. Well, you know it in English, not I think. The estimation of it, whatever. I don't know the terminology in English. The what? The variance, yeah, the variance. So that's the bottom line. If you're really interested, I can show you actually, I think even Corman has the actual has the whole full proof of it. But you could take that as a lemma. That is the sort time. How many times are we doing that? We're doing that n times. Therefore,
We don't need to know why it's 2 minus 1 over n.
no, that's given. Take it as given. Feltic. So now I'm going to fix this. I didn't fix this slide for some reason. I don't know why. You guys can't see. This should be theta. So therefore, the sort time for n buckets is what? N of O. Wow, what's going on here? This is not correct. Sorry. Let me just add here.
What does that mean when you do n of O?
I'll explain to you. Like it's n times. So basically, you'll have it updated on this PowerPoint's on the site, but I'll update it. This has to go here. I'm missing something here. Oh, I know why. It's in English, translation to English. So basically, it's like this. The bucket sort will work here. This loop here runs. You don't see this? You didn't see all these annotations just now that I wrote? Oh, yes, you do.
What? Yeah, we do.
Yeah, you do. Sorry, I was on the wrong screen. I'm using two computers just to see what you guys are seeing or not. Okay, so this loop here runs theta of n, right? Not O of n, it's theta of n. It runs n times, do it. We said that all these sorting cost me n times, right? N times O of 2 minus 1 over n. And the concatenation of the buckets cost me theta of n. I'll just go through the list. It's theta of n. So if that's the equation, how did I get to that equal to theta of n? Because think about this. 2 minus 1 divided by n is O of 1. Right?
Or multiplying by n.
Sorry, yeah, so it's n. So it's theta of n plus theta of n. So סך הכל it's theta of n. The 2 minus 1n is a kavod, that's 1. But this is a kavod, this is a constant.
Isn't it n times something over n? So that just goes away?
Yeah, so basically.
Right. Right.
Okay, so that's a better way of saying it. You're right, sorry. So this is a constant, obviously. So you're saying theta of n plus theta of n is theta of n. Right? I will update that slide 12. Okay. So let's take a look. Yes, that's to remind me. And that is to remind me to go to the guy that already got ready for us. Okay. So I've gone to this site actually because the visualalgo.net, it doesn't have bucket sort. So I'm showing you something here. Now, why did I bring you this one? Because if you notice, if you look carefully on the screen, the numbers here are whole numbers. Okay? They're whole numbers. Make the speed quite slow. Now, let's take a look. There's 29 numbers.
30.
Good. I was going like this. I was waiting for something to say. There's 30 numbers, right? From 0 to 29 here. Again, even when you see the visualization here, it might be a bit different than what I explained. But again, that's more for the visualization. The algorithm is the same algorithm. Here is our answer. Sorry, not our answer. This is B. This is B. All these empty lists. Yeah, same idea. Lists. 30 of them. Now, we're going to start, I'm going to start running it now. So it takes that first value and decides to put it in bucket 11. The value 374 went into bucket 11. How did it do that? Now, I'll explain. The numbers here, I'm telling you now, the range of the numbers, we said the range between 0 and K. K here is 999. Okay? I'm telling you the numbers here are between 0 and 999. I mean, 3-digit numbers. 999. So, take a look here. The linked list array index. Okay, my linked list array index. Which index to put it in is equal to the value 374 times the number of elements, which is 30. There are 30 elements. Oh, yeah, actually, it says it here. 374 times 30 divided by the maximum array value plus plus 1. So divided by 1,000. You might see sometimes without that plus 1. No, it's usually plus 1. Yeah, let's say. So then that gives me which index to put it into. And then we'll continue it. So he puts it in here in the list. I'll speed it up a bit more. So for each value, he starts looking which list to put it into. Now, this was a random list, by the way. He built a random list. I didn't build it. Random numbers between 0 and 999, we expect, depending on the random number generator, and this is something we talked about random numbers, how random are random number generators, all right? I think you probably did some type of question like that in the first semester. It's running a random to see how many times came out each number. You did something like that while this is working?
Yeah.
Yes.
Yeah. So again, this is really checking how well is the random number generator of this program, whichever one it used, and we can see how much it did. Let's speed it up even more.
So here it looks like it's sorting it as it goes along. Is that different?
Oh yeah,
from yours?
I'll talk about that in a minute. Yeah, I'll talk about that. You're very, very good point. Okay, now, whoever, I didn't see who said that, but that's very correct. This algorithm here inserted it already into its place. It didn't, when it copied it into the list, it already sorted it into the list. Now, there are two different theories about that. From one point of view, it makes sense. But from one point of view, it says, okay, wait, let's just do a whole, after we have all the values, then let's just do that insertion sort. And not just do it now while we're working. Which one's more efficient or not efficient? You can start doing a whole chakira here. But this is how they present it. It could be also visually, it was easier for them to do it that way. So I don't know. Now, take a look at this distribution. Not bad, quite nice. And then what happens is it continues and does, each one starts doing it and starts putting in the values. Now here, again, it put it back into A. You don't have to have the C. You don't have to have the values in the new one. But if I want to keep the original values, then okay. But here, I can just copy it back into the original A, and I don't need the C. Again, depending on your application, your algorithm, do you need to keep the original ones according to the original order or not? So you can do it either way. And let's just randomize the list again and run it very quickly. We are very curious to see what type of distribution there is. Oh, that was a bit quick. Hello. Let's do it again. Okay, this distribution is not as good for the randomizing. Again, let's take a look again. Let's do randomize, bucket sort. And
This looks even worse.
Yeah, okay. So this random is not very good, but actually it helps us understand how this whole concept of randomly, that it really shows you how the bucket sort, when it's good and when it's bad. If it's not, we want it to be distributed as much as possible, because then the lists don't get so high, they don't get so long. And actually, this is a nice way of looking at it to understand what's doing. Yeah, fair. Okay.
Is there such a thing
yeah.
as worst case? Because when we defined our bucket sort, we said it's defined for only a uniformly distributed list. So I guess, I mean, a worst case would be just make a straight line on one bucket. But I don't know if that's, do we consider that?
Yes, we do.
Or do we say it's not a
Yes.
bucket for, it's not
Right. So basically what we'll say is the worst case here, it will be n squared. Why? Because the sorting is going to cost us n squared. It will cost us n. It will be n squared. To actually sort, if I have a list which is up to n, it's going to cost me n. It's going to cost me n squared in the worst case, because I'm going to have to sort it.
But like even insertion sort has it's n squared's only its worst case. Like it could be a worst case bucket sort, but then be the best case insertion sort.
Yeah. Okay. Nachon. I'll
So
leave
it's like
the Tosfos. But if you're looking at the worst case, you're talking about the worst case. The worst case is that it's not sorted, right? You're talking about the best case and the worst case. Inside the worst case, you have different dargot. You have different targets, but that's a bit different already. Okay, that's bucket sort in a nutshell. That's how it works. The algorithm is quite nice. It's lovely.
So it's not necessarily linear.
No,
We're just hoping it is.
It's linear if you know the distribution of the keys. But you'll choose to use it if you know that pachot o yoter, right? That the numbers are uniformly distributed. That's when you'll choose to use it. If not, you won't use it.
Professor, but going back to the question someone just asked about if they're all in a straight line, so then you could just define the what do you call it, the k differently.
What do you mean by straight line? Explain to me.
I thought what was meant is, let's say that all fall into one bucket. So then
Into one bucket?
wasn't that the question of the
No,
worst
the question was that each list has only one element in each bucket. That's what he meant by one line. Each bucket has only one element. Doesn't go higher.
And why would that be then n squared?
No, that would be n. That's the best. That's classic.
What's the worst case when they're all
Worst case that all the lists are empty and one list has everybody inside it. The bucket is full with everybody. Everybody's inside one bucket. And all the other buckets are just empty waiting for somebody. There's nobody there.
So what that shows is that you could have just to redefine your, how do you refer to it, as the K? In other words, redistribute within that one bucket into further sub-buckets.
So then redistribute is already...
Oh, and they misread. How would that happen, I'm asking? Doesn't that just show somebody misread the...
yeah, basically you don't know what your data are. If you have no idea what your data is going to be like, you're not going to choose this. But a lot of times you have things which we do know mirosh, that there is some type of distribution depending on the application you're doing. If you know that there is some type of, if the numbers were randomly generated to begin with, for example, and the random generator is a good one, then definitely they will be distributed equally without some type of bias towards a certain number. Okay?
Yeah.
Good answer?
Yeah, thank you.
Good. All right. Now, yes, thank you. This is always to remind me what's going on, because just to yeah. Tough. What are we going to do now? We're going to go to here. I'll stop the share. Yeah, stop it and do a new share to the page that I did for you. Do this. And take a looky. I promised you some presents, guys, remember? So this is the present that I talked about last week. Where did it cut off here? Yes, I'll have to fix that. Sorry, I see here that it's not so. Okay. So basically you have a page with two sides to it. The first side has all 7 comparison sorts. Insertion sort, bubble, selection, merge, heap, quick, and binary. You have the key type, which all of them makes a difference what they are. You have, for each one, what is the runtime in the best case, the average case, and the worst case. How much extra space it takes. And obviously, in place or not is according to this column, but if you just want to look in place or not, you don't care how much. So you have that. You have if it's stable or not, assuming. And you have the description. A quick description just to remind you what happens. Now, you have all the different things. I wrote here tree sort because sometimes you might see that as a name, not binary sort, but a tree sort. It's a Ikeda. And you have here all the various values.
While we're on this page, could I ask a question?
Wait, how did that happen? Sorry. I'll have to fix this for you guys.
While we're on this page, I have a question about merge sort that I was thinking about.
Merge sort, yeah.
You say that its extra space is O of n, but doesn't it actually take up more? Because we take the whole array and divide it up into 2 subarrays. The total of that space is what
N.
we just did.
Which is
then
n.
But then we do it again. And we do it again. So it's more than n, right? It's like probably n log n or something.
You're saying no.
Because each call, doesn't it take up a new...
Yeah, each call... Okay, what you're saying is very interesting. It's a good thought. Every call, dynamic, every call will dynamically allocate smaller and smaller arrays, but it hasn't erased, you're saying, the previous ones in the recursive calls.
Yeah.
It's still there.
Because by the time we get down to the first 2 elements, we've already made basically all of our arrays.
You're making more than one array, but each array, like you're only making arrays of, the elements. You're not doing it of all the elements. So it's not.
But think about
really
on your first merge sort call. When you first call merge sort, you take your full array of n elements, and then you make 2 subarrays of n over 2 elements. But then you call merge sort on each of those. So now you're making 4 more arrays of n over 4.
No, stop. Just be careful. You're making 2 more arrays.
Oh, 2 more on each one.
Yeah, no, but when you come back...
Not at the same time.
Not at the same time, so... Okay, so 2 more, yes, not 4 more.
So it's 2 more. So it's 1 plus a half plus a quarter.
Yeah, so it's n divided by 2, and then you're going to make... No, but it's not 2, it's 1. N divided by 4, because only when you get up... It's, it does do it. It does do it, and n divided by 8, n divided by 16. So when I am implementing it, so theoretically you are correct that it's more than, but it's still going to be linear. It's not going to be edge squared. And you're saying maybe it's n log n extra space. Intuitively, I still think it's n. I'll look at it. I'll look into that. You can also look into it. It's an interesting question, but I think the actual summation will work out to be n in the end, and not n log n. Extra
But
space.
the arrays that you're making, they're not of size n.
I understand.
Every time you're making new arrays, they're getting smaller and smaller.
Well, okay, so log n.
You're still adding them.
Yeah, you're adding them, so it's going to be. Yeah, but the some amount might be n. So
I think it is n because
it will
because
be.
like the value like the sequence one half plus 1/4 plus 1/8 is
Right.
just 1.
Yeah, so it will be n in the end. Yes, it will be n. That's what I felt intuitively, but yes, correct. I totally agree with you. So if we're talking about n, yeah, it will be n. It could be that you'll have 2n, but 2n is n anyway, so that's the same thing. Okay, but what's really good about the question, it was a good question, because it shows how much you were understanding what's going on and really getting into it. Excellent, really good, very good. But in the end, it will be, because each time what's happening is you're going in each time. No, that's what's going to happen. Okay, let us continue to tell me now to do. Show them the sort summary. I did that.
Was there another side to that page of all the?
Oh yeah, yes, thank you. Yeah, see, we got carried away with the merge sort, and then we forgot to do that. Yes, sorry. So that was the first side. The second side is all the, I call them counting sorts, the 3 counting radix bucket. By the way, bucket sort, a lot of people call it a sister sort to the radix sort, because they're similar to a certain degree. Sisters, whatever, I don't know. So you have here the key types. Now, I wrote here all cases because basically most of them are all cases, but we do know certain things in certain cases that it's basically this is the official one. But if we're assuming that D and B are constants, then it's theta of n. Fine. And here we're talking about the bucket sort. If they're not uniform, it's going to be n squared. Extra space. And an explanation a bit if k is less than the complexity is less than n, the complexity is theta of n. This is what we talked about. So it's going to be theta n, but the official one is theta of n plus k. Excellent.
If it's not uniform, why is it theta of n squared for bucket sort?
And not O of n squared?
Yeah.
Because insertion sort is theta of n squared in the worst case. There you go. It's theta, it's not O. These, like I mentioned before, previously, I mentioned this to you guys, that in a lot of places, a lot of books, a lot of internet sites, you'll see that everything's written with big O and not with theta. Because it's not taught and they don't go into it and they say, look, big O, that's what's important. Geeks for geeks, or all these programming sites, not the academic sites, they use big O all the time. They don't go into theta or omega because they're looking at the worst case. If they're looking at the big O, what's the worst case? What's the maximum? Let's look at big O. That's what's important to them. So you'll see a lot of times more talking about O and not theta. These are more precise measurements because it is theta of n squared. But it's not better than n squared and it's not worse than n squared. So therefore it's theta.
Insertion sort can be better than n squared.
No, that's in the best case. I'm talking about in the worst case.
Okay.
Right, it's theta. Okay. Now, I had room on the page.
So theta usually means the actual case, and big O usually means the worst case. So what does it mean?
Not always. Big O is the worst case. I can also say that. Okay. Continue your sentence. Continue your question for a minute.
I'm trying to figure out is that what does that mean when you say best case, average case, worst case, and then inside there say theta, delta, or small omega or big omega?
All right. And when I'm looking at the data, I have a best for each different sort method. I know what is the best case and the worst case. Best case could be that they're all sorted. Okay. So if they're all sorted, it's going to cost me bloom. Let's say bubble sort. What's this? Oh yeah, a bubble sort. Best case would be theta of n also. Let's say selection sort. It's going to be n squared, even in the best case, because I'm going to have to go through them all and do it. I'm going to do it n squared, even in the best case. It's sorted. Let's say the numbers are sorted. The algorithm's going to go through each one, find the smallest, put it there, find the smallest, and swap it with the small. It's swapping it with itself, one after the other. That's in the best case. In the worst case, where it's sorted exactly the opposite direction, it's still going to cost me n squared. But there are algorithms that, if it's totally sorted, it's going to cost me this. If it's sorted exactly the opposite way, if it's randomly sorted, there are different cases that we have to look at. A quick sort or merge sort. Quick sort, brilliant example. The worst case is that it's sorted, and then we're taking the pivot value, always the last value, and then it's not going to be good. That's what we're talking about: best case, worst case, and average case. And when we talk about that case, we could say, what's its boundaries? Is it bounded by something? So some of them, we can only say it's bounded by, it's bounded by n squared, n squared, or n log n, or whatever it might be. And
So let's say bubble sort. Why is the average case O of n squared, not theta of n squared?
Exactly, that's what I was looking at now. I was just looking at that now, because I'm saying, "Oi, why is it O?" Because the average case includes. Pirkei Avos, we learn. Lo yodea omer lo yodea. I'm going to look it up. I don't have the answer in my head right now. I'll give everybody an answer about that, okay? I don't have an answer in my head right now why. The chayret should be theta. But for some reason, I wrote O for a reason.
In each case, in the best, average, or worst case, it should usually be theta, because since we're talking about a specific case, we know what it's going to be, no?
No, because let's say heap sort is definitely O of n log n, because that's the way that we derived it.
But isn't that also because since they're all the same? So
yeah, fair. Okay, nachon. Yes, theoretically, if this is theta and this is theta, then this should be theta. No, but
if that's O, the right one should be O.
Yeah.
The worst case.
Nachon. So it could be. The worst case is theta squared. So okay, chaval on time. I'll look into it. Okay. So you have here our sorts, and if already on the page, I put the algorithms of the three counting sorts, so you have it all connected and you have it all on one page. Now, if we're talking about all on one page, I had hoped, right now, you'll excuse me, I'm going to look at my telephone for a minute and see if I got a message or not. I sent an SMS even. No, okay. I've been trying to contact the course coordinator. I talked to him in the beginning of the week, and I made a suggestion in relation to all the different hakalot, helping out because of the corona business. I made some suggestions in relation to the exam. And one of them was to have an open book test.
Cool, I like that.
Yeah, I think so also. First of all, me personally, Every test should be open book. I don't have to test how good your memory is. Right?
We're having a test on campus.
Yeah. Tests are on campus.
So, like open book, would that mean we're allowed to bring computers, or we have to print things out
book.
beforehand?
Open book, no computer.
So we have to print anything out that we
Anything
want.
you want, yeah. Print or anything.
We have to have a hard copy.
Handwritten. Yeah, because we don't want you to be able to just Google stuff as well, obviously.
So we have to have a hard copy.
Yeah, only hard copies. It could be a book, right? It could be a comic book as well. And I'll tell you my famous joke. Once I know that it would be, hopefully, he agreed. He basically agreed. He said he has to check with the other lecturers just to make sure, right? But he liked the idea. So basically I say it's in Hebrew, Kol Chomer Ezer, Kolel Tehillim. You can bring anything you want, including Tehillim, right? So
you can't always bring Tehillim, even if they're not going to allow it.
No, it's closed Tehillim. It's closed book test, no books. You can't bring Tehillim. You have to do it from memory. So, okay. So, in relation to the test, once I know more details, for sure, I'm going to tell you. But we could say right now, Tam v'lo nishlam, meaning, as of now, we have finished seeing all the material in the syllabus of the course. Doesn't mean finish the course. But I remind you of our first meeting many masks ago, or many weeks, months ago. I said that I want to finish by the end of week 11 all the material, so we can spend week 12 to revise and look at previous exams. Week 13, we'll do a whole big summary. And Baruch Hashem, even with all this Corona business, we managed to do it. Not all the groups are going to finish by the end of week 12 even. My Hebrew groups also, we finished this week as well. And my girls group also finished this week. They finished already end of last week. Okay. Now, what's that mean? Very good. So what's it mean? The time now is 4, right? It's 4:06. I wanted to give you guys a break. Like I wrote to you in the email, we have to finish at 5 to 5. I have to be in a conference at 5 o'clock. This is very convenient. Instead of traveling to a conference, I could just do it from my Zoom. So I'm speaking in a conference, a couple of conferences now in the next few weeks. So it's a bit busy now. Okay. Do you want a 5-minute break or 10-minute break? What do people say? I want to finish by 5 to 5.
5 minutes now would be good.
Yeah, let's take it for Rega. So we do like this. Rega. Opa, Rega, go away. Okay, so we're going to make it 5 minutes, not 10 minutes. We'll have a 5-minute break. How's that? I did think about it, Miros. So right now it is 4:07, 4:12, we're back. And we're doing some exercise. We'll talk about what's down the road, and we'll start looking at exercises on sorting methods until 5 to 5. Okay, so let's take this break now. And I'll pause the. Okay, we have continued the recording. Careful what you say, it is being recorded, officially recorded. Okay, so what's happening? What's next? Before we continue doing some exercises, I don't want to get stuck in the middle of an exercise where we finish the time and then not talk about what's next. So we're going to talk about what's next for a couple of minutes, and then we'll start doing some exercises. So basically what's going to do is like this. Today we'll be looking at only exercises in relation to linear sorts. What we manage, we manage. Next week, what we'll be doing is we'll be talking about the final exam. All 4 hours, and it's a lot, I know. We're going to be looking, first of all, how the exam, by then we'll know exactly what the format is. It looks like it's going to be very similar to the format that we've had up to now, which is great. We'll be looking at previous exams. Now, in English, we have only 2 previous exams, right? You're the 3rd group that's done the course. So
But there's Moed Aleph and Moed Bet from.
yeah, definitely more elements. So we have 4 exams. Great. There are obviously a lot of stuff in Hebrew. And for my girls group today, I took a whole exam in Hebrew and made a whole PowerPoint presentation with questions and answers, and we went through it. I'll translate probably that one for sure, because I already have the answers ready-made, so I don't, set up as in slides. I'll be getting as many as possible into English. I also spoke to Adina, who's teaching the women's group. Maybe she'll translate one at least as well, so we can have as much as possible. The are in Hebrew. You could take Google Translate and translate it for those people that are having the troubles with the Hebrew. But obviously, it's not the same thing. I'll be trying to get you as much as possible up until the actual exam. In the Moodle site, you'll have the previous exams as well. I'll start putting them up, and that you can start playing with them. The main thing now is just to practice, and practice. One thing that's very important, and that's what I'm going to, take you to homework 10. And those people that have opened up homework 10, so there is homework 10. There is now homework 10 is very important. It's a very, very important homework. And I'll explain to you why. It puts it all together in relation to data structures. A lot of the questions will be, look, build a data structure, suggest a data structure that works in certain constraints. Constraints of memory, constraints of runtime. Where it's not only runtime, it says, look, it has to support the following operations, insert or find, or each one according to the data structure. And it tells you for each method, what is the constraint? It could be, okay, to find something makes no difference. But the insert has to be O of 1. Because a lot of times when you're building a data structure, you know what type of data you're keeping and how you're going to be accessing it or deleting and inserting. So it's very critical to me. It's more important for me to be able to insert quickly and, take out, it can be also n or n squared. It's less important. Or to find something, I want O of 1. I want to know the maximum value at O of 1 cost. That already tells you, ding, 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 maybe I'll build a max heap. Okay, well, what's the idea? The idea is that you have all this knowledge, your toolkit. And I'm reminding you something we talked about in the first lesson when I came out. I said, look, you have your tool chest. Some of it rusty stuff. And we added all these stuff into this tool chest. And now you're going to have to decide, here's a question. You have to build an algorithm, you have to build a data structure. You have to decide which data structure or a combination of data structures encapsulated together basically build your class with its methods and its attributes. Where the attribute can be a stack and a list, whatever. You can build your own data structure according to the needs of the constraints of the question. That's why homework 10 is a very important one to do. I'm going to work through at least one of them with you next week as well, because it's important to see. And we'll see that in previous exams, questions like that. Usually there's lately there's been one question, that type of questions. But again, in relation to types of questions and everything, we'll be seeing that next week. I'll show you the different types of questions and how it's built or whatever next week. But that's something that's important to know. So basically, just do practice questions. Find questions. Go on the internet. Find questions with answers. Try to go to academic sites more than Geek for Geeks, because not every geek knows the correct answer all the time. And you see that there's machlekes between them in the chat. But if you go to some academic sites, there's a place called MIT, for example. I think they're pretty good. Stanford, no. A lot of different universities. You can find stuff. There's no shortage of questions. Maybe I'll take from there. They're in English already translated. Oh, that's a good idea. So it's good. I'll find some questions from other institutions which are already in English, and that will just help us. So I don't have to translate too many. Okay. So that is what's doing there. Now, let us go back. No, we want to now go all the way. Yeah, I did that. Okay. Now let's take a look at a question. Now we're doing, sorry. Any questions about what we're doing next in the next 2 weeks? Okay. Take a look at the question. Start thinking about it.
For these, we're supposed to be using anything in our toolbox?
Yeah. From now on, everything is open. But here, this is a question in relation to, obviously, all the questions we're doing now are going to be in relation to linear sorts.
Professor, what's meant by pre-processed numbers?
Exactly. I was waiting for that. There's a whole concept in programming and building algorithms, which is called a pre-process. Sometimes I can do something which will, I'll do some type of a computation or something, do something on the data that later on helps me do things quicker. I'll give you an example. Let's say I'm writing some type of program algorithm, and I'm using some type of value that I need to compute inside a loop. Let's say I'm using, let's say, a cost of some type of item, which is based on a whole long equation. So I can compute that first and save that answer in a variable, and then just use, instead of each time inside the loop figuring out this value, I can just do it once, and it will save me performance time, right? Now again, we're talking about optimization. It's still going to be the same order of magnitude usually, but you want to write things in optimal time. But here in this question, we're saying, look, can you do something with all these numbers, these n numbers in the range of 1 to k, that after you do this business, you can return to me in O of 1 time how many numbers in the range between A and B, right? So basically our algorithm is going to get 4 parameters. A, the array, k is the numbers are between 1 and k, and 2 whole numbers, A and B, that we know that A is less than B. A is less than B. Anybody want to throw out an idea?
Can I suggest something?
Please.
Using the counter
Counter
sort,
yeah.
and you save the middle array when you save the counting numbers, and when you just search when the number starts, because you do n-1, so when you put everything in the array again, you know where he starts and when he's finished, the second number.
Yeah, but that's not going to be O of 1.
Isn't this exactly count sort?
Almost.
If I remember correctly.
You're right.
It lines things up in the pre-processing stage.
Yeah, good. Okay. So
you'll have the number of how many are smaller than it.
Yeah. Mm-hmm. No, definitely. You guys are saying correctly. So I can do the heart, the main kernel of counting sort. I'll do the first three parts. This is just a typo here. I'm doing those first three parts. And what do I have in CI now? In CI, I know how many elements, in CI, how many elements are less than or equal to me, right? That's the whole idea of the index, right? In that index 7, I know that in C7, that tells me how many numbers are equal or less to me. So if I do just this, I don't do the next stage of counting sort. I don't do that. That's enough for me to return how many numbers are between A and B. How many numbers are between A and B? Return what? Somebody? What am I going to return?
Minus B.
Almost.
GB minus A.
Almost.
CB minus CA.
Min plus 1. I don't know.
Yeah. CB, obviously, because B is bigger than A, but minus C of A minus 1. I want between A and B, including. So what do I have in CB? CB says how many numbers are equal or less than or equal or less than to me, to B. In A minus 1, I have the number of values which are equal to A minus 1 or less. I want to get rid of those because I just want to know how many are between A and B. So CB includes everybody. So take everybody and then just chop off all those which are from A minus 1 down to 1.
We also need to make sure that A isn't equal to 1, because if A is equal to 1, then we're asking for before the array. If we're,
yeah, okay.
But the number is 1 to K. So.
Yeah, the numbers are 1 to K. So therefore, no, but if A, no, he's talking about A. Oh,
say,
so
if we say
yeah.
C of A minus 1 and A equals 1, then we're asking for C of 0.
Inachinami. Great. Very good. Correct.
Well, so I'm not sure I understood that. A minus 1 is just like anyone tells you how many numbers are there between, let's say, 3 and 8.
Right.
So you'll do 8 minus 3 and you'll say 5.
No, yeah,
correct?
no. It's not how many, no, because it's the sum of C3, C4, C5, C6, 7, C8. You're looking at the values in each one of C. Each, right, has the number of appearances. Don't forget, the number of elements. That's basically what I want. Okay. Let's take a look at this question. The question that you asked in the beginning of today. Why doesn't radix sort work if the sorting method is not stable? So the answer is very clear. Because when we use basically what happens, when we're sorting according to DI, if we're not using a stable sort, the digits before that, from I minus 1 down to digit 1, again, LSD, they might change the order. They might. It doesn't have to be. They might. Here, for example, that's my array. I'm going to sort now according to the least significant digit by the 3, 1, 1, 2. Okay, hocus pocus, I sorted it. Let's take a look. Did I sort it? 1, 1, 2, 3, 3. Lovely. Obviously, they're not sorted yet because I haven't gone through the highest digit. So now I'm going to sort, what's the algorithm say? Sort it according to the largest digit here. 1, 2, 3, 0, 1. I'm going to sort it. Hocus pocus. And I sorted it. 0, 1, 1, 2, 3. And baya, great. I sorted it according to the digit. But if I look at the numbers now, what do you see? You see that 13 became before the 11 because the sort that I used to be able to sort the digit wasn't stable. Therefore, the 13 was able to jump ahead of the 11. Maybe yes, maybe no, but It can happen. And therefore, that's what can happen here. It's not good for us because we didn't use a stable sort. Okay? I promised you an example. Here it is. Is there somebody who needs a clarification why we have to use a stable sorting method? Now's the time to ask. You can also ask later on, but you can ask now. Okay. Next question. Wow, video questions you guys asked. That's great. I'm glad. Okay. We have strings. And just for simplicity's case, we're going to say they're all lowercase letters. They're all lowercase. So, how do you sort them in Overventai? Suggestions, please.
26 letters. 26. Oh, wait a minute. It depends on the base. That's why.
You're saying to use a radix, a radix?
Possible. One option.
Yeah, possible. Yes, good. Good option. I like that. I like that option. It's nice. Sounds good.
Especially because the radix, it does it based on as you said, based on each digit. So that'd be very helpful for words.
Nice. Good. Excellent.
But there's a difference of the size of the words.
Yeah, it doesn't say. The strings might be in different lengths. Correct.
In radix, did we have to like concatenate zeros onto the front of things that were smaller?
Yep.
Yeah. So let's also do that here.
Exactly. Lovely, Ellie. Good. Lovely. You guys.
So you said 27, base 27, because we also need some idea of a zero character?
Yep.
Uh-huh.
Okay, it's more than that. Not exactly. Yes and no. Two reasons. One, think about it. When you have a base n, how many digits are in a base n?
N minus 1.
How many digits? No, n. Base 10, you have 10
digits.
digits. The range of the numbers are from 0 to n minus 1. Base 10, the digits are from 0 to 9. Base 2, it's 0 to 1, but there are 2 digits. Base 16, you have 16 digits between 0 and f. Okay? So if I say base 26, which is fine, then I'll have between 0 and 25. That's going to be my values. And then that means with the arrays, I'm going to have to start doing minus ones all the time and stuff. So why don't I just do from base 27, and then I take the ASCII and I have it, okay, that's 1 to 26. And now if it's a blank, if I have to start appending these type of blanks, that can be in 0. So, and because when you sort things, just think about when you sort in Excel or anything, or even, you know what, think of your class list. And when they're sorting it according to, not the letters here, but according to the Teudat Zehut number, your ID numbers, right? All the people with the passport numbers, which is shorter than the Teudat Zehut number, show up beforehand, even though let's say yours starts with a 9, your passport number, you're going to show up before somebody with a 2 beginning and his Teudat Zehut number, because it's a shorter string. So also with strings, Kohen is always going to be shorter. They're always going to be before Babashvili, right? Because Kohen's a smaller string. Okay, so how are we going to do it? So first of all, we have to find what is the length of the largest string. M, we'll call it M, which is a constant. That's the largest string. We could
Wait. We want Cohen to be before Bashvili in our sorted list?
Yeah,
because that's not like alphabetical as we would think about it.
It is lexicographically, sure. Isn't? Oh, sorry. And Rega, if I'm saying that I want it, yeah, why? Oh no, sorry. You want it in in the same one. Cohen and Babashvili was a good example.
If I have
Yeah.
two last names, Gold and Goldstein, I want
Yes.
Gold to be before Goldstein.
You want gold before Goldstein. Good, great, thank you. That's a better example. Sorry, that's a correct example. What I gave example wasn't correct. Gold and Goldstein is a correct example. Thank you. We're going to take each letter in base 27. That means A is 1, B is 2, Z or Z is 26, and 0 will be a 26. Of 0 to 26, where A is 1, sorry, the range is between 0 and 26, and A is 1 until 26. And now we have to do what I think Menachem, I heard somebody and a few people said that, we have to pad. We're going to have to pad extra zeros to these numbers. We're going to have to pad it with extra zeros because we want them to have the same length. If we're going to sort according to the digit, we're sorting numbers. So I'm going to have to add all these extra zeros to these numbers so they all have an equal length of M according to the larger string. So I have a 0 at the beginning. Fine.
Now that's not included in the previous step because that
No.
N.
Here I'm translating all the numbers into all the letters into numbers. But now I have to also make sure that I have extra zeros for all those ones which are shorter. Gold, I need to add, I'll need to add to the gold also extra zeros there.
So the next step is again O of N because you're saying you have to rerun through everything and search everything and then.
Yeah, it's
first
all
of all,
that,
wouldn't
yeah.
it
It's
be
O
more
of
than
N.
O of N because it's O of N plus, whatever's less than. It's
Yeah,
really.
but
I don't know.
it's O of N. But to build the algorithm to do that, it's O of N. I just insert it. I just have to go through all of them, right? But I have to go through all the strings or all the representations already, and I'll do a if, and just add zeros if I need be. So that cost is going to be O of N, because I'm going through all of them. That's N. I have N numbers, N strings.
Oh, I see. So we're not doing it by each digit, each letter.
No,
We're doing
not yet, not yet.
Okay.
And now this is this is not a pre-process. This is this is like a type of pre-process. This is getting it ready. I'm taking the data and getting it ready to be able to do this radix sort. That's what's happening now. But all these 3 steps was to be able to do a radix sort, where the number of digits is M, the base is 27, and then I'll just do a radix sort. And a radix sort, we know it costs me of the theta of D times N plus B, right? That's the runtime. D of N plus B. That is the runtime. But we can see that M is a constant, B is a constant. So just like we said, if B and M are constants, then it's going to cost us O of N.
Where do we put the zeros? We put the zeros on the front or the end of the strings?
It will be on the front. Why the front? Because basically we're making numbers, and you want to sort it. We're sorting from the least significant digit. You're not putting it at the end because then you have the zeros there. You want to put it in the beginning.
But if we put zeros at the front, then like you said, we'll have Cohen in front of.
Yeah, right. Let me just check. Maybe I'm saying it the reverse.
Cohen is supposed to be in front of Goldstein.
Maybe
We'll have a shorter string in front of a larger string.
So
matter even if that shorter string has a greater value.
I feel like we want them as the least significant digit.
Yeah, sorry, Lechon. So definitely, we want it to be, because we wanted it sorted. Sorry, you're padding at the end. Here we'll be padding at the end, not padding in the beginning. Correct. We'll be padding at the end. We'll be padding at the end the zeros. So therefore, when we're sorting it, and that will stay, but later on, it will get according to the actual. So Cohen will be after Babashvili, but gold will be before Goldstein because it's stable. Okay, excellent. Very good.
Yeah, because gold has a lot more it's just gold followed by zeros, whereas Goldstein
Exactly.
is
Where
gold
Goldstein,
followed by some other values,
which are
followed
higher,
by zeros.
which
Yeah,
are higher.
just
Excellent.
higher than zero.
Correct. Don't forget, there's another stage where we have to take those numbers and hocus pocus, make them back into a string, which also the cost is going to be n. So the whole business is going to cost us O of n.
Theta.
Yeah, that really, it's going to be theta, I think. I would start playing. For some reason, don't know why. It's not here. If I'm not mistaken. Okay, I'm going to look now. This is an older version. I changed these to thetas, some of them. So, okay, because this is theta here, not O. Okay, but if this is the question, can you sort in O of n time? That's the question, right? So definitely, if I write here O here, that's fine. I could be more medaic and even write theta, but if I'm answering the question, then definitely what I wrote here is correct because I'm answering the question. Do it in O(n) time? Yes. You know, this is O(n), this is O(n). That it's also theta, but it's definitely O of n as well. So I am answering the question. We have time for at least one more, probably two. This is really an interesting question. You have n numbers. Here's my n numbers. Array A with n numbers. Ramban. N numbers. The range is between 1 and n cubed. How would you go about it? How do you suggest that we, what would be the most efficient way of doing that?
I would say bucket.
Bucket. Give me,
When
in
you say
Hebrew,
efficient, do you mind that it's not at all space efficient?
I want efficient in relation to as runtime, space, and no problem, whatever you want.
Yeah, I think bucket would be the best one.
Well, we're doing it as uniform, is it?
Oh, great. First of all, Pinchas David, RTQ, read the question. He says, look, I have no idea about the numbers except that they're whole, and here is the range. I don't know that's a uniform distribution.
Right, but if we have a big
And,
range,
what? Sorry?
if we have a big range, then we can probably tend to the average case that there are probably more
No.
normal, have a
No.
normal distribution.
No. Oh,
This is a trick question because this array is sorted. Got it.
no,
So
it's not sorted.
What array this is? Is it
Okay, that would be cute, but no, it's not sorted. No, but what's the story here? What's the story? We have here a range of numbers. Now, to start doing a bucket sort, for sure, bucket sort, you know what? I'll even say that the bucket sort is the buckets, let's say they're uniformly distributed, but then I have a problem. I'll need n cubed buckets for n values. So for sure it can't be uniformly distributed. Again, we have n numbers, n elements to sort. You know, take the n, sort them. I'm telling you now that there's n cubed values. So you're going to make n cubed buckets. For sure you can have empty buckets. So bucket sort's not going to work. Huh? So basically, if we're starting to think about it, if I take any type of comparison-based sort, how much is it going to cost me? Choose a baby. Choose whatever you want. It's going to cost me n log n. N log n. So maybe that's the most efficient one. How much is counting sort going to cost me?
Isn't that omega?
Omega?
Oh, you said
Okay, you
O
said
of n log n. Is it that's worst case or that's best case?
No. יפה. when we're saying in the worst case, you can't go, when we say it's omega, that was saying basically you can't do better than. But the worst case will be n log n. In the worst case. But in general, we can say it's O of n log n, right? That would be the best thing we can do. A quick sort, merge sort, heap sort, they're all n log n. But you can't do better than n log n. So you want to write here omega. You know what? Not a bad idea. Okay. Okay. So, can anybody do better? Counting sort. How much is counting sort can it cost me?
O of n plus k, but k is really big.
So therefore, count sort is going to cost me O to the n cubed. Why? How did we say? What was counting sort? It's n plus k. The k here is n cubed. So n plus n cubed is n cubed. So count sort is even, in Hebrew, more dafuk. That's not good. That's not good at all. Okay.
How many,
Okay, let's take a look at radix sort. Or bucket sort. Let's look at the next ones. A radix sort. How much is that going to cost me? Let's take a look. My base is 10. How many digits do I have in a number that goes up to n cubed? I have 3 times log n to the base 10. How did I get to that? Just take a look, think about, and this is stuff that you basically did in first semester when you talked about the number systems. Think about, let's say take base 10, right? That's easy for us, right? Now, let's say n was 10, right? If n is 10, n is 10. No, n is 10. No, I want n10. I don't want n10. I want to get to the following. Basically, what we have is we have ones, tens, hundreds, thousands, right? That's how it works in base 10. Each digit is for the ones, the tens, the hundreds, the thousands. Now, how many digits am I going to have in n cubed? In n cubed. So let's say I have 10 numbers. N is 10. What is n cubed? Somebody? How much is n cubed? 1,000.
Yeah.
1,000, right? 1,000. So the number of digits that I need really would be the ceiling of 3n, n cubed. I'll take the 3 down, right? And I'll take the log, but this is from n cubed. I'll take the log, and this will tell me how many I'll need. To get to the number 1,000, I need basically 4 digits, really. Because the 1,000 is a 1, 0, 0, 0. So now the maximum number of digits I'll need is 3 log n, about to the base 10, not to the base 2. Here it's very important to write the base 10. Therefore, what is the radix sort going to cost me? We said d. D is the digits. Digits cost me log n, log 10 of n. The 3 makes a difference to us, that's a constant, times b plus k, b plus n, or n plus b. So
it's n log n?
Sorry?
It's n log n?
So in the end, it's going to work out n log n, because log 10, from our point of view, it's n log n. So radix sort here, in this case, because n cubed is such a big number, because of these digits, we're going to get n log n. So radix sort's no good. So basically, we've come to an answer that the best thing that we can do is n log n. Can anybody suggest b'chol zot, a kvetch? B'chol zot, a kvetch. Okay, I'm looking at the time, so I'll present it to you guys. It's nice, watch this. We're going to use radix sort, but we're going to do something beforehand. I'm going to change. Huh? what's this base 10? This is not correct. Base n. It says here base n, not base. Sorry, guys, my mistake here. It says here base n.
So that it becomes linear.
Now I'm going to convert everything to base n. Now we'll run radix sort. Let's take a look. All the numbers in the range are in the range of 1, 2, n cubed. So the maximum number of digits is going to be 4. No more than that, because they're up to n cubed. So I have the ones, the n's, the n squareds, the n to the power of 3. So the largest number is 1000 in base n. That's if I take the number n cubed in base n, the number is 1000, 4 digits. And if I would have said that it's up to n cubed minus 1, we could have gotten away with 3 digits. Just because of that one time that n cubed, I need 4 digits. Otherwise, 3 digits would be enough. And then, no problems. The runtime will be this. D is 4. My B is n. My base is n. So it's 4 times n plus n. Bravo. O of n.
It's not actually faster than what we wrote up above, right? It's just defined as faster.
Sorry?
It's not actually faster than what we have on the top left of the page, is it?
Yeah, it's dividing into more
Definitely.
pieces.
Definitely.
Doing more at the same time.
Because this is
Order of magnitude faster.
obviously we're talking about if we're talking about large n's, yes, because you could say in certain cases, because I'm doing all this process here, I have to I'm going to do here a process that's going to cost me n, right? You're saying here, this costs me n to do this, right? So maybe the n log n will be quicker, but again, we're talking about orders of magnitude. This is n, and not n log n. N log n is slower than n.
But this n log n is locked to the base 10 of n. It's not even locked to the base 2.
Yeah.
So it might work out that the counting sort.
Okay, so basically what you're saying, the counting, yeah, but no, but even still, this is one girsa which doesn't work. This works. But I was showing you that radix sort in the base, when we're using base 10, is not going to be good. Dafka, a counting sort with n log n to the base 2, log to the base 2 is going to be better than log n here, definitely. Will it? No. Okay, whatever. So what did we see here? We saw a nice chapim, how we can use these sorts. Again, if the keys are like that, we can use these type of sorts depending on what we're doing. Let's wrap up for a minute.
We haven't talked about what the process of changing a number's base is. Is that hard? Is that easy?
No, it's easy. It's easy.
It should be O of 1.
No, but yeah, it's O of 1. But
the algorithm is like what's that like?
Yeah, it's O of 1, but you're going to do that n times.
Yeah.
Okay, but it is O. It's just multiplications and divisions. It's yeah. Okay. But the relevant question, that's something you have to ask, right? Okay, what did we do today? We talked about the linear sorts, counting, radix, and bucket. Those are the 3 types of sorts. Lovely. We also started looking ahead. What's going to be next? And if we're going to take something from Parshat Shavua this week, hey, oh, I'm sorry, it's not what's supposed to be.
It's okay in America, whatever, in Chutzlar.
Oh yeah, Chutzlar. Okay, the guy whoever's in Chicago right now, he's not watching, he's not live, but yeah, fair. But definitely, the pasuk that we want to say is Nachol, Nachol, La. But yes, we can do it. No, that's not nice. Definitely, we can do it. It's doable, and just like we can liyaresh haaretz, we can also do in the course. That's one of the main things here in the course. You'll be able to do it, and we'll just survive, and definitely it's doable. Tov, kol tov. As in Hebrew, they say Shabbat Shalom or Good Shabbos. Question is no. I'm gonna have to stop the discussion now because I have to get to this conference. As Shabbat Shalom. You can send me emails. As you know, people are writing to you all the time. Emails, I answer. Kol Tov, Shabbat Shalom.
Shabbat Shalom.
Shabbat Shalom.
Thank you.
Shalom, thank you.
Bye.
Shabbat Shalom.